entropy. We've seen several formulas for this so far. We've got the original definition just in terms of number of microstates. We've got the formula involving heat. This one's often more useful because usually it's easier to measure the amount of heat and the temperature than to try and count up the number of microstates. This is specifically if the temperature is constant. And or delta S is approximately heat over average temperature if temperature is changing only a little bit. And the borderline between a little bit and a lot kind of depends on the situation and how much accuracy you want. In the situations I've had experience with, it seems like as long as if you're only changing temperature by like maybe 50 or 60 kelvins or something, this formula is going to be accurate to within like a 20th or a 100th of a joule per Kelvin or something like that. This is remarkably accurate unless you're doing very large changes in temperature. If you're changing by like hundreds of Kelvin, or if you want extreme accuracy, you want to use the actual formula delta S exactly equals heat capacity times logarithm of the ratio of temperatures, final temperature over initial temperature. So this formula is exact if the temperature is constant. This formula is exact if the temperature is changing, but this one works as a pretty close approximation if the temperature is changing, but not a huge amount. And of course, all these temperatures have to be in kelvins for this to work, so that 0 actually means something. Any questions on those formulas so far? So as an example, let's say we have a container of water. Let's actually say we have, let's say 3 kilograms of water and we want to freeze it. 3 kilograms of liquid water at a starting temperature of, let's say, 20 degrees Celsius. Or let's go ahead and put that into Kelvin, 293 Kelvin. And we want to freeze it. We want to turn this into a block of solid ice. At a temperature below the freezing point, let's say 253 Kelvin. So let's say this is the process we're dealing with. We're going to take this warm-ish water and turn it into cold-ish ice. If we want to figure out how much we can see how much the temperature changes. It's just going from 293 down to 253. So we could actually list out these values. T initial equals 293. T final equals 253. But if we want to make a graph of this process on a temperature versus entropy graph, if we want to actually keep track of what's the entropy, what's the temperature, we know we've got temperatures at 253 and 293. But we want to figure out what entropy is involved there also, or at least how much the entropy changes from start to finish. So how could we do that? How could we figure out how much the entropy is changing here?
Using the formula where temperature is changing, so delta S is equal to C
Yeah, the temperature is definitely changing. So we'd want to use T final over T initial. So that would be 253 over 293. And the kelvins over kelvins cancels out. And what could we use for heat capacity? How do we usually calculate heat capacity if we know the material? We could just use mass times specific heat. Yeah, because the heat capacity is mass times specific heat or number of moles times molar specific heat, either way. Mass is going to be 3 kilograms. How would we figure out specific heat?
Is it 1/2 R times the number of modes?
If we know something about the number of modes, yes. In this case, though, or also that would be molar specific heat rather than the specific heat per kilogram, which is what we would need here. But yeah, in this case, we could look it up. This is a known substance. This is water. So we can just look up specific heat for water. The problem is, if you look up specific heat for water on a data table, you're going to find different values for specific heat of liquid water and specific heat of solid water. The different phases have different properties. So we can't just use liquid heat or liquid water specific heat. We can't use solid water specific heat. This formula isn't really going to work because the specific heat changes. Also, it's not just removing heat to make the temperature go down. This isn't only a temperature change. What else is changing here? Yeah, we've got a phase change. So we can't just use this one formula and be done with it. We can't just say this is a substance changing from 293 to 253. It's not only getting colder, it's going through a phase change as well. So we're really going to need to treat this not just as one process, in fact, not even just as 2 processes. We've got to split this up into 3 processes. Because the first thing that happens to the liquid water, you start removing heat, and what's going to happen to it? The very first thing that happens if you remove heat from liquid water. It gets colder. So we can use this formula to represent the process of getting colder. Once it hits 273 Kelvin, though, 0 degrees Celsius, you remove more heat, and what happens? Right, it's going to start freezing. And we can't use this process for this formula for the freezing process because what do you know about the temperature during the process of freezing?
No temperature change.
Right, no temperature change, it stays constant. While it's in the process of freezing, it starts freezing at 273 Kelvin. It finishes freezing still at 273 Kelvin. And then it continues cooling off to 253. So during the process of freezing, we can't use this formula. What formula would we have to use instead? Yeah, Q over T, because the temperature is constant during the freezing process. So we're going to use the logarithm formula during the temperature change process, the Q over T formula during the phase change. We don't even need T average here. It's just the temperature while it's freezing because it's constant. And then another logarithm formula during the temperature change for the ice. So we really need all 3 of those processes: the liquid cooling down, the phase change, the freezing process, and the solid cooling down. Each one of those involves its own delta S. So let's calculate each one of those separately. We've got the freezing process, or the cooling process. Liquid cooling off. We've got, for that we can use the heat capacity times logarithm of the ratio of temperatures. Delta S equals mass times specific heat times logarithm of T final over T initial. Mass is going to be the 3 kilograms. Specific heat of liquid water, that's what, 333.5, I think? Liquid water, no, that's the heat of melting. 4.18 kilojoules per kilogram Kelvin times logarithm of, and in this context, what should we use as the initial and final temperatures?
293 and 253.
Sorry, what was that?
253 over 293.
Does the liquid water end at 253?
Oh, wait, no.
Because remember, we're just talking about the liquid water cooling off to 273. So the final temperature of the liquid, because we're only talking about the liquid cooling, is 273. And the initial temperature of the liquid was 293. Kelvins and kelvins cancel out. Kilograms and kilograms cancel out. And the kelvins canceling out is especially important. You can only take the logarithm of a unitless quantity. Units don't really work well with logarithms. So the units have to cancel out for this to work. So we get 3 times 4.18 times logarithm of this ratio. Can't do logarithms in my head, so I go to a calculator. 273 over 293. So negative 0.887. And the units there, what would be the units that remain here? After we cancel everything else out, what are the units? Yeah, we've got kilojoules per Kelvin because the kilograms cancels out. And since this is less than 1 anyway, we might want to just multiply by 1,000 and put it in joules per Kelvin. So negative 887 joules per Kelvin. Delta S is negative. Entropy is decreasing. How would you justify that? Why would we say, why does it make sense for entropy to be decreasing during this process? Why should we expect from the start that entropy is decreasing here? Partly the temperature is decreasing, but more to the point, yeah, heat is leaving the system. We're making the temperature decrease by removing heat. If you remove heat from the system, there's now less energy for it to play with. Less energy available means fewer ways the energy can be arranged, and that means lower entropy. In general, you remove heat from the system, you decrease its entropy. So entropy has decreased by this much. After we cool it to 273, we keep removing heat, and what happens? It's 273, we remove more heat, and what does this liquid do? Yeah, it's going to go through this phase change. It starts freezing. So the freezing process, the phase change itself, during the phase change, during the freezing process or solidification, it's not changing its temperature. Its temperature just stays at 273, which you can even see on the three-phase graph from way back at the beginning of the quarter. Three-phase model, energy added versus temperature. During the phase change, the temperature stays constant. So we're starting here, we're freezing it, but we're not changing the temperature during the freezing process. So temperature stays the same, but we are extracting energy. Because of that fact that the temperature does not change, we can use delta S equals heat over temperature. Temperature is, of course, going to be that 273 Kelvin. And again, note that this has to be in Kelvin for this to work. And what about heat? How could we figure out how much heat we're removing during that freezing process? What type of energy are we changing? Yeah, this is just the bond energy change. So we can use our usual delta M, delta H. So off to the side, we could just say heat equals delta E bond. More formally, we would start by writing delta E total equals work plus heat, but there's no work involved. And delta E total is just delta E bond here, because that's the only thing that's changing during this process. For that, we'll use our usual delta M, delta H. And we want to use, as usual, mass of the higher energy state, mass of liquid. How much does the amount of liquid change from start to finish? How much liquid do we start with and how much liquid do we end with? We start with 3 kilograms of liquid. We end with how much liquid? Yeah, we're changing from 3 kilograms of liquid to 0 kilograms of liquid. So delta M is going to be final 0 kilograms minus initial 3 kilograms for a delta of -3. So delta M is going to be -3 kilograms. That's where that negative comes from mathematically, because we're subtracting final minus initial. And then delta H for water, I think that's a 333.5 kilojoules per kilogram. Kilograms cancel out, we're left with -1,000.5 kilojoules. So that is the amount of heat involved in the freezing process. Any questions on that heat so far? And then we divide those, -1,000.5 divided by 273. And we get about -3.665 kilojoules per kilogram, or kilojoules per Kelvin. Again, convert the kilo to 1,000, we get -3,665 joules per Kelvin. Again, that's a negative change. That's still a decrease in entropy, which we could explain thermodynamically by saying we're removing heat, so we should expect the entropy to be decreasing. We can also look at this in terms of number of microstates though. When you're freezing the water, what's happening to the individual molecules? If you're going from liquid to solid, how would you describe the behavior of the individual molecules? What's changing there? They're moving slower, or moving slower I would say is more about temperature. There's definitely less motion because when we're changing, I mean, why do we call this bond energy in the first place? What's happening with the bonds? Are we forming bonds or breaking bonds? Yeah, we're forming bonds. We are making these particles more bonded together. Previously, in the liquid form, they were partly bonded, but they were still more free to move around each other. They just couldn't really leave like they would in a gas. But they're somewhat bonded, but they're able to move. When we convert to a solid, they're much more tightly bonded to each other. They can still wiggle, but they can't really flow around. So by adding in more bonds, by forming more bonds, we're restricting the freedom of motion. Less freedom of motion, more restrictions on the motion mean a lower entropy, because entropy is all about microstates. If we decrease the number of ways they can move by adding more restrictions, then we've decreased the number of ways that can be arranged. We've decreased the total number of possible arrangements. So forming bonds is always going to end up decreasing the entropy. Of course, there might be something else happening at the same time that increases the entropy even more. But in this case, the fact that we're removing heat guarantees that the entropy is decreased. Any other questions on the freezing process so far? So we finish freezing it, we keep removing energy, and what happens? Cool it off, freeze it, keep removing energy, and what's going to happen? Yeah, it's going to decrease in temperature. The solid is going to cool off. So for the solid cooling off, let's see how that looks. For the process of the solid cooling off, it's a change in temperature, so we want to use the MC logarithm of the ratio again. Delta S equals mass times specific heat, that is the heat capacity of the whole object, times logarithm of the ratio of temperatures. So we've got 3 kilograms of ice. Can we just use the same 4.18? No, we're going to have to use the one for solid water, which is 2.05. Yeah. 2.05 kilojoules per kilogram Kelvin times the logarithm of the ratio of temperatures. And in this case, what are the final and initial temperatures involved for just the solid cooling off? Yeah, it started at 273 because we're only going from the fully frozen, but still at 273 down to 253. We're not talking about the whole process, just the solid cooling off. So the solid ends at 253, but the solid started at 273. Again, we get some units canceling out in very convenient ways. And we are left with 3 times 2.05 times the natural logarithm of 253 over 273. So I'm getting about negative 0.468 kilojoules per Kelvin, or multiplied by 1,000, negative 468 joules per Kelvin. So those are the changes in entropy involved with each one of these processes. Any questions on that so far? And while we're at it, let's also try the approximation formula. Delta S is approximately heat over average temperature. How can we figure out how much heat is involved during this process of cooling off the ice? Yeah, this is a change in thermal energy, so we could treat heat as mc delta T over the average temperature. We already calculated m times c, that's just a 3 times 2.05, so that's 6.15. Delta T from 273 down to 253 is negative 20. And what's the average temperature, or how would we calculate the average? If we start at 273, we go down to 253, what's halfway between those? Yeah, 263. So if we multiply that out, 6.15, that's from the 3 times 2.05, times negative 20 divided by the average temperature, 263, we're getting about negative 0.468. Rounded off to 3 decimal places, it's exactly the same. If we actually take it out to a few more decimal places, we do see a difference. This is negative 0.46768. Whereas this one was negative 0.46791. So they are a little bit different if you go out to the 4th decimal place, but 3 decimal places of accuracy is probably more than you need for most practical applications anyway. So the Q over T average formula is a little bit off from the exact value, but for only 20 degrees of temperature difference, it's remarkably close. This is a very close estimate. So if you're only talking about maybe 10 or 20 or 30 degrees worth of temperature difference, and you don't really care too much about accuracy, if you don't need to be absolutely exact, Q over T average is going to be remarkably close to the actual value. So if you're in a situation where the temperature is only changing by maybe up to 50 degrees or something, and Q over T average would be much easier to calculate than MC, logarithm of the ratio, then go ahead and go with Q over T average. But if you want the exact value, use the logarithm formula. And of course, if the temperature is not changing, then you should just use Q over T. That is the exact value. Any other questions on that so far? So let's see if we can graph this. Now that we've got all this information, let's see if we can put this on the temperature versus entropy graph as a process. Because this is going to be very similar in some ways to the pressure volume graph. You represent the state of the system right now as a point on the graph, state of the system later as some other point, and then the process itself is some path leading from the initial point to the final point. So filling in the values we've got, we know when as the liquid cools, the delta entropy is negative 887 joules per kilogram or joules per Kelvin. During the freezing process, delta entropy is negative 3,665 joules per Kelvin. And during the solid cooling process, delta entropy is negative 468 joules per Kelvin. So we can convert these into points on the temperature versus entropy graph. Let's see if we can sketch that out. The only important temperatures we need to care about here are 293, 253, and also what other important temperature in between. Yeah, so let's mark all of those. 253, 273, 293. And those should be evenly spaced. And of course, this has to be in Kelvin in order to make sense. For the entropy axis, we're going to have entropy measured in joules per Kelvin. And the thing is, entropy, the actual value of entropy, we don't really care about. We didn't calculate how much entropy each of these cases has. We just calculated how much the entropy changes. So we can't really mark a number for entropy, but we can at least mark how much they change. Are we starting at a higher entropy or lower entropy situation? At the very beginning, when we have warm water that's liquid, is that high entropy or low entropy? Yeah, that's high entropy, because we know that all these processes involve decreases in entropy. So presumably we're starting at high entropy and we're decreasing the entropy in these three processes. So I'm going to mark some high starting value. I'm just going to call this S0, the starting entropy. We don't really have a number for this, so I'm just going to mark it as an unknown constant, S sub 0. But we know we start at S sub 0 entropy and 293 Kelvin. So that point right there, this is the starting value. This is warm liquid water. Liquid H2O at 293 Kelvin. Let me just call that warm water, actually. This is warm water. And then we're going to cool it off. As we cool, it decreases to 273 Kelvin of temperature. And also what happens to the entropy? Yeah, as we cool it off, the temperature decreases. So we're decreasing the temperature, or entropy decreases. So we're decreasing the temperature and decreasing the entropy. We should be going down and to the left on the graph. So that should be going to 273 in terms of temperature and transitioning to the left because we're decreasing entropy. In fact, we even know how much we're decreasing entropy to. Again, we don't really have a number, but we could at least mark on the graph S0 minus 887. So whatever the starting value is, we subtract 887, and that's the value right now. So this value of entropy and this value of temperature, this would be cool water. We've transitioned from warm water to cool water. And can we tell what path we're going to take here? Do we know if this is going to be a curve or a straight line or several straight lines joined together or anything like that? It might be linear. The only problem is we don't really know what this process was. We don't, I mean, if you go back to the pressure volume graphs, like let's say you had 2 points on a pressure volume graph. What about the process tells you what sort of path you connect it with? Like whether you should connect it with a curve or a straight line or zigzag or what? What is it about the process on a pressure volume graph that tells you how those points should be connected? The amount of work done, specifically how much of the, I mean, the 2 points determine the change in energy, but that change in energy might be all work, or it might be all heat, or it might be a mixture of work and heat. The exact path you take for both pressure volume graphs and temperature entropy graphs depends on what path you take, or how much of it is work and how much of it is volume. In this case, we didn't really talk about, or sorry, heat and work. We didn't really talk about how much is heat and how much is work here. We know that we're removing a certain amount of energy to cool off the water, but we didn't really specify whether that was heat or work. Or some combination. So we don't really know what path is taken. We're going to have some path from warm water to cool water. For the moment, let's just assume it's a straight line, though it doesn't have to be. We don't really know for sure what shape this is going to be unless we know how much is heat versus how much is work. For the next process, though, as we freeze the water, as we freeze it, what happens to the temperature? Yeah, the temperature stays the same. So on the graph, the freezing process is just going to be a horizontal line, which means we are not changing the temperature. We do change the entropy, though. We go from S0 to S0 minus 887, and then we subtract another 3,665 beyond that. So another 3,665. Is going to take us to, so we take S0, we subtract 887, we combine that with another minus 3,665, and we get S0 minus 4,552. From just combining the minus 887 and the minus 3665. So that would be the entropy when the water finishes freezing. So here we have cool ice. And this one we know is a straight line because the temperature does not change during that process. This one I would actually expect to be more of a curve. Not sure exactly what curve, but some sort of curve. And then what happens next? We remove some more heat, and what happens? Yeah, the temperature is going to decrease. We're going to drop from cool ice to even colder ice, 253. And we also know how much the entropy decreases there. Originally, we lost 887 joules per Kelvin. Then we lose another 3,665 joules per Kelvin. Then we're going to lose another little bit, another negative 468 joules per Kelvin. So that's going to be this final entropy, which we can calculate just by subtracting another 468 here. So the 4,552 we've already lost. Tack on another 468 and we get S0 minus 5,020. Because overall we've lost 5,020 joules per Kelvin. So that puts us at final temperature, final entropy right here. This is cold ice. And again, the exact shape of the path is going to depend on how much of that was heat versus how much of it was work. Presumably, it's not going to be a straight line, though. It's going to be some sort of curve. So this would be an example of a temperature entropy graph, a TS diagram, that we're showing each situation, each state as a point on the graph, and the processes that take you from state to state as paths on the graph. Any questions on that so far? Why is it curved? The curve represents, the exact shape of that path represents how much of that process was heat and how much of that process was work. And there's a very specific curve that goes along with all heat and another specific curve that goes along with all work. In fact, if it's all work, if there's no heat at all, what would you expect to happen to entropy if there's no heat, if it's only work? Our basic formula for a change in entropy was heat over temperature. If it's all work and no heat, yeah, we'd end up with 0. Entropy would be constant. So what would that look like on the graph? If there's no heat transfer, then entropy is not changing. What would it look like on the graph if entropy doesn't change? Yeah, that's going to be a vertical line. So on a temperature entropy graph, a vertical line means no heat. As opposed to on the pressure volume graph, what would a vertical line represent? Right, on the pressure volume graph, a vertical line is an isochoric process, no change in volume and no work done. On the pressure volume graph, a vertical line means no heat, an adiabatic process. And likewise, a horizontal line on a pressure volume graph means no change in pressure. On the temperature entropy graph, a horizontal line means no change in temperature, an isothermal process. So this is one of the very important distinctions between these graphs. For a pressure volume graph, an isothermal curve is going to be a complicated curve. On the temperature entropy graph, an isothermal process is just a horizontal line. So there are certain processes that are complicated curves on the pressure volume graph, but simple straight lines on the temperature entropy graph. And there are other processes that are simple straight lines on the temperature entropy graph, but complicated curves on the pressure volume graph. Specifically, the temperature entropy graph makes easy straight lines out of an isothermal process, or if there's no change in heat, or no heat, that would be an adiabatic process. So in a process, an adiabatic process, no heat transfer, only work, that's going to be just a simple vertical line on a temperature entropy graph, because no heat means no change in entropy. Entropy stays constant. Whereas on a pressure volume graph, that's going to be a more complicated curve. So certain types of processes become much easier to analyze if you choose the right graph to represent it. And in fact, in many situations, it's a good idea to draw both a pressure volume graph and a temperature entropy graph for the same process to get even more information. Curving the graph when there's a change in temperature, usually yes. It's possible for it to be a straight line, but only if it's a very specific combination of work and heat. Like I said, the exact path taken depends on how much of that process was heat versus how much of it was work. If it's all work and no heat, it's going to be a vertical line. If it's all heat and no work, that's isochoric, and that's going to be more complicated, I think. Some sort of curve. But in general, the only time it would be a vertical line is if it's all work and no heat. It's going to be a straight diagonal line if it's a very specific combination of work and heat. But in most cases, it's going to be some sort of curve. The straight line would be only for a very specific combination of work and heat in terms of the ratio. But also another comparison we should be making, on the pressure volume graph, the area under the curve represented what? What specific information did you find from area? You got some curve on a pressure volume graph and you find the area under the curve. What did that represent? Yeah, the area under the pressure volume graph is the amount of work for that process. And if you find the amount of work as the area and you know the amount of change in energy from the initial and final points, then you can just subtract to find the heat. For the temperature versus entropy graph though, let's try that same approach here. Specifically, let's take a look at the isothermal process, this flat line in the middle, because flat lines are much easier to analyze area. If we take a look at just this isothermal process in the middle, this flat line, and we look at the area under just that section, ignoring the curves. Flat line, area under the flat line means we just get a rectangle. And how would you calculate area of that rectangle? Yeah, that's just the width times the height, right? We got to be careful about deltas though. The width is definitely a change in entropy. This width is how much the entropy changes from initial to final. The height though, is that height a change in temperature, or is that a change? Is that height just the temperature? Yeah, this is just temperature. In this rectangle, the height is the temperature right now, 273. That is how high the temperature is from the axis itself. So that means our temperature times delta S tells you the area. And we could actually calculate that. That's a change in entropy of negative 3,665, temperature of 273. We could multiply those together. But more conceptually, since we know this is isothermal, what formula did we use for delta S? What's our delta S formula if temperature is constant? Yeah, that's just heat over temperature. Multiply those and what happens? Yeah, temperature cancels out. We just get Q, the heat. So the area under the curve here is the heat. So we've got this very nice sort of an echo here that for the pressure volume graph, the area under the curve represents work. For the temperature entropy graph, the area under the curve represents heat. So if you've got both graphs, temperature versus entropy graph and pressure volume graph for the same process, it becomes much easier to find both work and heat. Heat is the area under the temperature entropy graph, work is the area under the pressure volume graph. And it turns out this even works if it's not isothermal. Even if you've got some complicated curve, as long as you can find the area under that curve all the way down to the axis, that tells you the amount of heat involved during that process. And this is why I was saying that the exact shape of the curve, exact path you take, depends on how much is heat and how much is work. If you're using the same sort of initial and final, but you're involving more heat and less work, more heat would bulge this up so it encloses more area under the curve. So the exact shape depends on the amount of heat versus the amount of work involved in that process. Any other questions on those temperature entropy graphs? And if you want to get some more practice with this, the FNTs don't really have all that many problems on temperature entropy graphs, but they've got a lot of problems from previous FNTs on pressure volume graphs. If you want to get some more practice, go back to those FNTs about the pressure volume graphs, look at each process individually and see if you can redraw that process on a temperature entropy graph instead of a pressure volume graph using the same information. So give that a try and see if you can make sense of the connection between those two types of graphs, and I will see you next time. You're welcome.